Hi, welcome to the March 2022 webinar of the MIT Alumni Energy, Environment, and Sustainability Network, EESN for short. Today, can hydrogen be a bridge to carbon-free electricity? First, let me just say a little bit about EESN. For over a decade, EESN, the network has been bringing information about our changing environment and energy systems to MIT alums and other attendees. These themes are closely tied, and today they're cross-cutting with the topic of climate change as well. EESN's second goal is to connect alums. As a problem solver engineer, originally engineer, I know how collaboration can be a powerful tool in meeting our third goal, which is to act and make progress towards a sustainable future. So I think today's topic will contribute to that. We encourage everyone to visit our website. Aside from webinars that we do every month, we have an ambassadors group, a climate education and advocacy group, and a more recent climate business and innovation group. At the end, we'll mention some of the upcoming events. Next, Sarah Simon, class 72 and EESN core team coordinator, will introduce our speakers today. Following that, we'll have their short presentations, and then we'll have a Q&A from the attendees. We'll remind you to use the Q&A feature. The chat room is, the chat is not activated for the session. The panelists will be able to put information for you all to see in the chat, but for the dialogue after the presentations, use the Q&A panel. Having said that, over to Sarah and our guest speakers.
Thank you, Ramon. I see that we're still collecting some attendees. We have almost 100 here today, which is very exciting for us. This issue of hydrogen is a really big one. It's a form, we're going to be using it as a form of energy storage. In a way, we've used it as a fuel and a food for forever. The food chain is an energy storage thing, and it uses carbon and hydrogen. It is the most common element in the universe, and there's a lot of potential for using it in a clean energy way that is not putting out carbon emissions. So we have two really great alumni speakers today. It's very exciting getting these events together and meeting these people. First, we'll hear from John Gaertner, who I forget exactly the way he likes to put his title. He's a consultant and strategist. He started off, he has his master's from MIT and started off in the nuclear business, but his involvement with the electric power industry has been a constant thread for him. He worked for a while on where did it go? He worked for a while on right inside the utilities, and then went to work for more than a dozen years for the Electric Power Research Institute. He's looked at risk assessment and how plants can improve, and today the industry still calls on him as a consultant as they're trying to make their plans for a clean energy future. Our second speaker is Jeff Benoit. He'll speak right after John Gaertner, and we'll have questions after the two of them. He does Power Systems Manufacturing and has done it at, no, that's the name of his company. He is at Power Systems Manufacturing, which is a Hanwha company. He does strategic planning and market analysis and sets up the value propositions for the companies. This comes from a long history of commercializing gas turbine retrofits. He worked at GE in their turbine unit when he first started his career. And he's been working very hard on how gas turbines get retrofit more cleanly. Right now, he's coming to us from Brussels, Belgium, because he's at the annual European Turbine Network meeting and the workshops that they're running there. So we ask you to put your questions in the question place. We will chat with you and provide a few links. We will talk with you after, and we hope you will join EESN to continue these kinds of conversations. But right now, for hydrogen and our clean energy future, I'd like to present John Gaertner.
Thank you very much, Emily. And thank you, Sarah. And I'm very pleased to make this presentation today. And so I won't be controlling them, right? So I'll tell you to move forward. So next screen, please. Okay, we've been asked as panelists to address two questions. One is, what is the role of hydrogen in zero carbon electricity generation in the future, in our clean energy future? And secondly, will the supply of clean hydrogen be adequate to support both the anticipated increased electricity generation and strong use of hydrogen in transportation? Of course, we can't answer those questions completely, because the future for hydrogen is complex. And I mean complex in the mathematical sense, which means it's uncertain and it's evolving rapidly. But our purpose here, I think, is to establish kind of a common base of knowledge, and or as I say on the slide here, put us on the first rung of the ladder of knowledge. Next slide, please. So this is a picture from the Department of Energy NREL laboratory, Renewable Energy Laboratory, and it depicts what the low carbon hydrogen economy should or could look like in the future, say 2050, when we expect our environment, our energy environment to be quite clean of carbon. If you step back and focus on that large blue circle with H2 in it, and then the picture begins to look like a sort of a distorted wheel, with that H2 circle being the hub, a hydrogen hub, and all around it are applications and interfaces to that hydrogen hub. On the right, the lower right-hand corner, are three purple circles that really depict the current use of hydrogen. Almost all of hydrogen is used today in the chemical industry, the petroleum refining industry, and for fertilizers and ammonia. If you look in the upper right, those depict the transportation usages, which are quite low today, but expected to grow. And the rest of that circle is sort of distorted blocks, which represent the interfaces with two major energy infrastructures. One is that big red circle, which is the electric grid, and the other is that large tan circle on the bottom, which is the gas infrastructure, which represents pipelines and storage facilities and blending facilities. And it's really the interaction of those three infrastructures that we're going to be talking about for the rest of this hour. Next slide, please. This slide begins to answer our first question, what is the potential role of hydrogen in electric generation in the future? The left-hand side of this slide shows really the first half of this relationship, and it's called power to hydrogen. Hydrogen, as Sarah exists, is everywhere in the universe, but it's not in any useful form on our planet. So we have to make gaseous hydrogen from water or other chemical reactions. And two ways of doing it are depicted on the left of this chart. On the top, we can make hydrogen using clean electricity. And I indicate that renewables, wind, solar, or geothermal, or nuclear power are candidates to take either excess electricity or low power electricity, because it's not needed at the moment for sale to cover the electricity grid loads. And we use that to power an electrolyzer. Sort of remember high school chemistry when we stuck two wires in a beaker and watched the hydrogen and oxygen bubble up. Well, these electrolyzers do the same thing, but in a very much more sophisticated, technically advanced way. They're highly catalyzed reactions. They might use high temperature steam, especially if they can get very high temperatures, say from a nuclear reactor. And they create that hydrogen. And then we go over then to the third column, and we store that hydrogen either in tanks as a compressed gas above ground, or we can store it in geological places like salt domes or depleted oil and gas fields or rock caverns. Or we can take that hydrogen and put it in a pipeline and use our hydrogen as an energy carrier to take it off to where we can use it or store it at a distant location. The other alternative on the left-hand side is we can use natural gas to make our hydrogen, but that is a reaction that emits carbon dioxide in large amounts, and so that's unacceptable in the future. So if we use natural gas in the future, we'll need to use carbon capture and storage to remove that carbon dioxide, and that is a technology that is currently not commercially available. So after we've created that hydrogen and we're in column 3, then when we need it, we can store it for hours or days or even months. That's the beauty of the hydrogen. And then we can remake electricity with it through the use of gas turbines, either using them in a simple gas turbine cycle or in a more efficient power plant, which uses a combined cycle. Jeff is going to tell you all about that. So I'm not going to spend a lot of time on that particular application, but I do want to say 2 additional things. One is that this whole process is not 100% efficient. So if you're going to take energy and make hydrogen and then hydrogen and make electricity again, it's about a 50% efficient process. So that's why the electricity has to be inexpensive to begin with, because you lose half of it during this process. And secondly, that even though this is the most dominant use of hydrogen and electricity, there are many other ways that hydrogen can be used. And I indicate those on the little red line on the bottom of this slide, but I'm not going to go into them for this talk. So next slide, please. So the next question was how much hydrogen is needed for electricity, say by 2050. One could do some back of the envelope calculations from data available on the web, but those don't work in these complex systems. You really need sophisticated modeling and simulation. And luckily, there are people doing that modeling and simulation. And I'm going to use one case study to make our point about how much hydrogen is needed. Duke Energy, which has a service area in the states of North Carolina and South Carolina in the United States, and they have a much larger service area, but this particular case study, I'm looking at just those 2 states. They did a sophisticated modeling and simulation analysis, and they came up with what they thought their generation mix would be in 2050, and that's indicated in that top box. You'll see that renewables and nuclear energy will make up the majority of their generation, and that's clean already, so we don't need to mess with that. The second line shows that there's 2 other components. One is advanced generation, which they call ZELFRs, which stands for zero emitting load following resources. And that's a type of generation. It's very important to the utility, but those technologies don't currently exist. And hydrogen is one candidate to fill that need. And then over to the right is still, even in 2050, they're afraid they may still need to have up to 6% of fossil fuel use just for handling peak loads. Hydrogen can cover both of those 2 that are indicated in yellow, but I hypothesized that they would want to replace the peaking completely, but they would probably only want to replace or use hydrogen for half of their other advanced generation because they like diversity. You don't put all your eggs in one basket. So I've depicted that scenario in the bottom block below, in the box below, by the line that's shown in yellow. If you go all the way to the right, you'll see that it says that that Duke would need 6,000, those are megawatts of hydrogen capacity in order to meet that need for hydrogen. And that is hard to visualize. So what I did is I said, how can I make it visually accessible to you? If you imagine that electrolyzer would be at that time probably 120 megawatt device. We would need 50 of those devices scattered throughout the state of North and South Carolina in order to supply that much hydrogen. That's a pretty big lift, but it's not unimaginable, and it seems like we should be able to achieve that with effort. So that's how much hydrogen would be needed for that application. If I were to scale that and say that the Duke situation is representative of the whole country and scale that up to the size of the United States, we would need to multiply the hydrogen capacity by 6.5 times what we currently produce. Again, a big lift, but not unimaginable, not too unreasonable. It turns out that the International Energy Agency has made a sophisticated modeling and simulation forecast for the entire globe, and they came up with a factor of 6 increase. So it kind of corroborates our little case study here. And by the way, they indicate that they think 62% of that would be green hydrogen, or hydrogen from renewables or nuclear, which isn't really called green, but it's clean. And 38% of that would be from blue hydrogen or natural gas, but with carbon capture and storage. Next slide, please. If we add transportation in, we're not blessed with that kind of knowledge because we don't have good modeling and simulation, because we don't have consensus on exactly how hydrogen is going to be used in transportation. But we do believe that most of light electric vehicles will be electric. And we do have projections, as I indicate on my red sentence, the first red sentence, where utilities have projected how they would handle that in 2050 if 90% of electric vehicles were electric. And we already know the hydrogen impact of that because we calculated that on the last slide. So light vehicles are not going to be an additional problem for the electric utility industry. Medium and heavy vehicles, and that includes really rails and marine shipping, however, is a bigger problem and may not be able to be electrified. Maybe it might go directly to hydrogen. And if it did, that would cause our requirements for hydrogen to go up by an additional 20%. So an additional 20% of the 600% that we're predicting. So again, it's a big lift, but it doesn't sound, since the 600% is already a big estimate, it's sort of round off error to add another 20% onto that. So again, it isn't an alarming number, but certainly a challenge. Next slide, please. So I think we answered the 2 questions to the best of our ability, but I wanted to bring up a couple of important issues. One is the cost of green hydrogen. It's currently in the range of $3 to $6 a kilogram to make, and it's projected it needs to be $1 to $2 in order to be cost effective commercially. And the good news is that the Department of Energy has that as one of their goals for this decade, is to work on reducing that cost to that $1 to $2 price range by 2030. The second issue is the one I brought up earlier, which is if we're going to use natural gas, which currently makes almost all the hydrogen, if we're going to use that along with green hydrogen, we need to learn how to capture the carbon from it. Now, it's easier to capture carbon in a electrolysis process than it is in a power plant because it's much more concentrated. So that is hopeful, but we don't have commercial means to do that today. And finally, we're going to need to have these hydrogen hubs so that we have an infrastructure in order for this to happen. Electric utilities are not hydrogen companies, and transportation companies are not hydrogen companies. So we really need an infrastructure to be built. Next slide, please. So in conclusion, I think that we've shown that hydrogen can be a bridge to carbon-free electricity, although a challenge. We've shown that we would need to increase by 2 times to 7 times the amount of hydrogen we currently make by 2050. but we have the technology to do that, or we have the technology in progress in development to do that. And finally, we will need these hydrogen hubs to develop the infrastructure. And again, those are in process. And I think Jeff's going to talk a little bit about that. And if he doesn't, we'll have time in the discussion to answer any questions you have on that. So that's what I have to say about that. Thank you very much.
Thank you, John. That's great. Now we're on to Jeff. Let's see what kind of slides he's got. There we go. Thank you.
Okay. Well, thank you very much, everyone. And it really is a pleasure to be here. Thank you, Sarah, Amy, and Ramon. And John, thanks for that presentation. I wanted to talk a little bit about what I believe is a great opportunity with gas turbines utilizing hydrogen as part of the fully decarbonized grid. But I wanted to just quickly give you an idea of my company. As Sarah mentioned at the beginning, I work for a company called PSM, Power Systems Mfg. We're based in Jupiter, Florida, but we are a global company. We are an aftermarket service company for the global fleet of gas turbine power plants. So we perform the services on OEM gas turbines. So if it comes from GE or Siemens or Mitsubishi, we have the ability with our own technology and have for the past 20 years offering our own solutions to help our customers maintain their business objectives and their profitability, as well as their reliability. One thing that we've noticed with our customers is a strong focus over the past 2 to 3 years on environmental, social, and governance rules, ESG, and sustainability plans. And with the sustainability plans, they talk about a reduction of their carbon intensity of their assets, of their power generation assets. And many of them have set 2030 objectives, and many have set 2050 objectives. And many of them have said net zero by 2050. What has changed in the past year is a movement forward of looking at how tangibly they can begin to look at the remaining assets that they have in their fleets. Many of them have retired their coal plants. Many of them have input and installed much solar and wind. That's one way. Efficiency upgrades are another. The one remaining piece is how can you get the same type of carbon intensity reduction with gas turbines? Well, I'm going to build the case for it. If we look at what we're seeing in the renewable world, where we've gone from the 15th century to today, where we now have 14 or 15 megawatt wind turbines that are offshore and providing power. And then we also have photovoltaics. And in this particular case, that's a 10 gigawatt field in Australia being used to generate electricity. So what do you do with this highly volatile, this intermittent power? How do you back it up so that way your lights stay on and you do it on a grid scale? Well, I believe the way we're going to be able to do this is with the gas turbine. First of all, it's very flexible. It's dispatchable. Natural gas in a gas turbine is one of the cleanest of the fossil fuels. And also gas turbines are very versatile when it comes to fuel, such as hydrogen, and I'll talk about that. One thing with all of that renewables is sometimes you can't use it all. So wouldn't it be great as an energy storage mechanism, which Sarah brought up, is to take that excess renewable and through an electrolyzer, generate hydrogen and use that as a basis of energy storage that can be released on the grid through gas turbines when you need it. Also, there are great, we're focused on our retrofits for the combustion gas turbines. And this is a way to do it, but remember, it's going to take certain regional market drivers, global market drivers, legislative policies to help frame up this hydrogen value chain. Now, one thing I wanted to show you a little bit is the opportunity with hydrogen, and I have pictures here provided courtesy of TU Delft, which is one of the universities that we work with here in Europe, where I am this week. First of all, zero carbon emissions, but with hydrogen, but you have to worry about oxides of nitrogen, which is a concern. And this again allows us to balance the flexibility needed for the grids. Here in Europe, tremendous amounts of wind and solar being put on the grid. Gas turbines are the natural way to do it. The challenge is, as John brought up, was the high cost of production right now, but recognize that the hydrogen value chain is nowhere near the scale that we currently see with renewables, and it needs to follow that process. And what we're seeing is tremendous amounts of investment for blue hydrogen as well as green hydrogen. One thing I will tell you here is blue hydrogen will be the bridge to green hydrogen in the United States, primarily because we have so much natural gas, it just makes sense. And one thing I wanted to show you, just look at the flames as they move. The left is natural gas, the right is hydrogen. And look at how quickly the hydrogen flashed back in that tube. That's one of the challenges if you're looking at using existing combustion technology rather than starting on a new platform. One of the things to understand is the topology of hydrogen, and we're going to focus on three of these: green hydrogen through electrolyzers, blue through steam methane reforming of natural gas, for example, and then with nuclear power, curtailed nuclear that could be used through an electrolyzer as well. I'm going to give a couple examples of white, which is in many cases refinery off gas. But I'd like to introduce a retrofit of a combustion technology that we're working on. It's called the flame sheet. And it provides tremendous flexibility for customers today, and it's being installed today, and they're doing it for tremendous range improvement in terms of operation. But it's also future-proof because it's highly capable of doing a wide variable blend of hydrogen, and today upwards of 60% hydrogen by volume, which is about a 28% reduction in the carbon intensity. So it is, this does provide a way to future-proof the existing installed fleet of gas turbines. Now, just to give a little bit of the technical background, it's a unique platform. It utilizes 4 different fuel circuits, just like stages in a car transmission. It has 2 recirculation zones where the flame is anchored in the combustor, and it's done with a trapped vortex method, which gives it very good stability margin. On top of that, the velocities inside here are very, very high, which is something that is helpful because of the high reactivity of the hydrogen. And this can be dropped in right into an existing OEM gas turbine, and we're doing that today. One of the things we do have to do is we have to be able to push these designs as far as we can, sometimes to the point of destruction. And you don't do that in a customer's gas turbine. You do it at a test facility. And we utilize a world-class test facility to test these combustion system retrofits at full condition across a myriad of operating conditions and a myriad amount of fuel, from not only hydrogen, natural gas, liquid fuels, and now looking at ammonia as well. But this is where we push the design, so when they go into a customer's machine, we're confident it'll work. We currently have these combustion platforms that we design operating. This is a gas turbine in Louisiana, which is only operating 5% hydrogen by volume, but it's limited by what's being provided by the chemical plant next door. And then another chemical plant with a power plant right next door generating steam for chemical processes, which is a variable 0 to 25% hydrogen by volume, but we've tested it up to 35% very successfully, again, with very low NOx emissions. That's the real key here. We're not reducing NOx emissions with water. This is done as a function of the technology, and we're doing it dry. In terms of the flame sheet platform, we have 10 of these installed already in the United States. It provides not only, as I mentioned, the significant improvement in operational range, but very low NOx and CO emissions. And it has the capability of up to 60% by volume of hydrogen today. Some very exciting news for this is how do we push it? I mentioned 0 to 5%, 0 to 25%. We do have a customer in New Jersey, JERA, that will be installing this flame sheet into a gas turbine, which will be provided refinery off gas from up to 40% hydrogen by volume to achieve their decarbonization objectives in that gas turbine. So it supports the Phillips 66 refinery as well as JERA's zero CO2 objective as well. And then also with our parent company, we are building a power plant that will utilize this flame sheet combustor, and that will look to push it to up to 50% hydrogen by volume. Again, that will be with refinery off gas, and we're doing that with Coepa, which is one of the power generation entities in Korea. So the question is, of course, I want to fully decarbonize gas turbines. They can be and will be fully decarbonized. They must be, to be that underpinning firming capacity for renewables. The more renewables that go on, the more volatility one gets in the grid. You need that dispatchable method and energy conversion device, such as a gas turbine, to take care of the volatility. And with a 0 to 100% hydrogen, in this case 100% hydrogen, you now have fully decarbonized that asset. So it is similar to what a renewable is in terms of its carbon signature. Today, as I mentioned, we're looking at 60%. We do have a roadmap towards 100% that we're actively pursuing. Many in the industry are talking about 2030 to be ready with this type of combustion system for new gas turbines. We see the entire fleet of installed gas turbines around the world that can support this type of combustion system, completely retrofittable. It's simply a matter of where do we get the hydrogen, which again is the challenge that I just wanted to talk about. One of the things, actually two of the things that we're seeing now. One is a huge push by the administration to set up hydrogen hubs. This is $8 billion to effectively kickstart the hydrogen value chain, that supply chain, and all of the challenges needed to drive cost and cost down, scale up, technology in, to drive to $1 per kilogram of hydrogen within 1 decade. And that will put it within the realm of competitiveness, and recognize that there will need to be a carbon mechanism, price on carbon, if you will, what I call a price to pollute, which will also be part of that. But again, it's across not just power generation, but industrial applications, transportation, and where the focus areas are going to be. So we're very excited about that. Finally, one of the things here today, granted, the huge amount of hydrogen isn't available at scale yet, but with refinery off gas, that's the low-hanging fruit. We have tremendous experience there. What I would tell you is that we are at the pilot and demonstration stage, and we're seeing operators and customers coming to us looking for these type of demonstrations. What they want to see and they need to see to support their sustainability goals is to be put on the pathway a very reasonable, well-thought technology pathway to fully decarbonize that asset. It would be a shame to simply not use it and decommission it when it can be repurposed and revitalized for the future. And with that, I'd like to thank you very much for your time, and I look forward to questions that you may have. Thank you.
Thank you, Jeff, and thank you, John. We have been getting lots of questions, and I'm going to start with the first one. Well, a lot of them are about the hydrogen supply. So if the two of you don't really have good information on that, please feel free to say so. The very first question that is still on our list here is, given the failures of carbon capture and the finite amount of natural gas, which I'm not sure there really is finite amount, why would we even consider this path to product hydrogen? Perhaps John or Jeff, what would you like to say on that?
Well, I can speak. I think it's the question is relative to blue hydrogen and the fact that in order to get blue hydrogen, you need to do some carbon capture and carbon sequestration. I think the big reason for that is simply because of the tremendous amounts of natural gas that's being produced in the United States through the fracking technology, which has been quite a disruptive technology over the past decade. And what I see is that it should be a bridge to full green hydrogen. So it's a matter in the United States of how big that window is going to be. Today, there are many companies, oil and gas companies, also chemical processing companies that have not only hydrogen infrastructure, but they're investing in hydrogen pipelines, hydrogen generation as blue hydrogen, as well as CO2 transportation to where it can be sequestered. So that's the first thing. Here in Europe, I would say that window is going to be much, much smaller because there is no natural gas here in Europe. It is being imported, but the big push with the recent RE Europe H2 program is that they will aggressively go after green hydrogen and keep the blue window as small as possible.
Thank you. That was from Andy Silber. YY, whoever you are, has also asked whether, has also mentioned that the blue hydrogen may have higher emissions because more natural gas is used to power carbon capture. Of course, that's true in the United States. Europe, I don't think, uses quite as much natural gas for power. But John, if you have anything else to say on that issue of blue versus green and whether we can do it, do you have some things to add there?
I don't know whether this is technical or political, but I think that the main push has been to use green sources for the electricity, not the blue. But in order to get the money for these hubs and in order to get the support from all the states, we really needed to compromise. And the compromise is to really give a try to this use of gas and carbon capture. And that's really why the hubs, for example, there's a requirement that at least one of the hubs makes its hydrogen from blue sources, from natural gas. Excuse me. And there's another requirement that at least one of the hubs blends hydrogen with natural gas in a pipeline. And there was a question I saw related to that. And they said, well, how's that going to work in the long run? You know, there are industrial uses that can blend, can use a very high blend of hydrogen or even 100% hydrogen, but can we put that into retail homes? And that we have yet to prove. So I think these were great questions, and they are really important unanswered questions at this time.
We have a lot of questions, and we're going to try to get to as many as we can, and provide a way afterwards for those that don't get answered to be shared with the speakers and try to get at that. One interesting question that I hadn't heard someone bring up before is how much water do you need to meet the hydrogen requirements? Any thoughts on that?
Yeah, I can give just a little bit. Certainly, I understand that the issue with water and hydrogen. It takes about 10 liters of water to generate 1 kilogram of hydrogen. So that's pretty much the ratio that one gets. And you know, I think to go to green, yes, I think with efficiency improvements in electrolyzers, I think with the scale being done, it will help with the overall economics. When it comes to water, you know, it's going to be a matter of it needs to be placed in these electrolyzers, for example, needs to be placed where there is plentiful water. And that's what's going to happen. You know, you're not going to put it necessarily in areas where you don't have access to water. That just simply doesn't make sense. But it is something that will need to be addressed as well as we move towards green. So.
Okay, there's a lot of discussion about ammonia, using ammonia as the transmission mode for hydrogen and also the distribution lines. Jim T. Omega Wind has asked about ammonia tanks and storage, and I'm scrolling through pictures here, but let's start with that. What role do you guys believe that ammonia might be a good way to make this hydrogen supply? What are the benefits?
I think that,
Sure. John, do you want to go?
well, I'll say something about it. I'm not an expert on these things, but I think that ammonia, if we're going to ship energy by long distances, say by water, ammonia is a way to to do that. But replacing electric transmission, for example, not so sure that ammonia would be cost effective for that.
Yeah, if I could add on to that, John, I've over the past couple of weeks, I've been at a number of energy conferences, some with oil and gas and exploration and production of hydrocarbons. Blue hydrogen is very big and will be used to generate ammonia, not only for fertilizer, but also for transportation on a global basis. What I've seen is a demand in Asia, Korea, Japan. They are putting together not only their decarbonization strategy on a country basis and investing heavily, but they're also looking to be a tremendous off-taker of ammonia. So you can use the blue hydrogen, you can generate ammonia, you can transport it long distances. In the United States, it can be by rail, it can be by pipeline, but obviously with ships. And then it can be reconverted into hydrogen for whatever purpose. In this case, my use case is with gas turbines. I think if I could ask the one question I get answer the one question I get asked quite a bit is, well, why don't you just burn ammonia in a gas turbine? The answer is you, of course, can do that. As I mentioned, gas turbines and combustion systems are incredibly flexible. On a retrofit basis, it's very problematic simply because that fuel-bound nitrogen generates inordinate amounts of oxides of nitrogen, which is regulated by the government. It's a health issue. It creates smog. So it's regulated to very, very low levels. And we're talking about orders of magnitude if one is to consume ammonia in a gas turbine. The other way is post-combustion treatment with a selective catalytic reduction device, which again, you're injecting ammonia through a catalyst to reduce the oxides of nitrogen. But that's one of the challenges, but I do see the industry driving to do in huge volume blue ammonia.
We see a question here from Phillips, I don't know how to pronounce it, Schmelzel. How would one transition a gas distribution grid from fossil gas to 100% hydrogen? Seems like a lot of equipment switches would have to be done in tight coordination, possibly down to household levels. I'm not sure.
Yeah, and that was also asked up here by how hydrogen pipelines can be made safe for urban areas. And again, if you guys have looked into this, fine. We were not here to talk about hydrogen supply today, but let's have at it.
Yeah. I can go ahead, John.
The Electric Power Research Institute has a major program, and they're working with the Gas Institute. It's a collaborative thing, and they're they're looking into how to transition the methane natural gas lines into a cascading of lines all the way from 100% hydrogen down to what could be used in homes, and even replacing some of the what we currently call natural gas with a synthetic natural gas that might be considerably greener because it could come from biogas and that sort of thing. So, but I don't see any answers to that question yet, even though there's significant research going on. We can really see the bubble for the things that Jeff and I talked about. These technologies have great promise if there's the resources put into it and the commitment on the end users to use it. But for the gas, I think that's the degree to which we can save the gas industry in its current form is still unknown because of those questions that the listener posed. You know, you can't. It is considerably more dangerous, and none of the equipment that's in homes and businesses are equipped to run on higher concentrations of hydrogen. And now utilities are willing to make the commitment, the engineering costs and the technology changeover costs, but residences and commercial operations may not be able to do that.
Yeah.
By the way, I'll mention to the listeners and the viewers, we have a lot of questions. A number of them are being answered, and if you go to the Q&A chat box, the Q&A box, they get moved to the answered tab. So that's one place that some of the questions that have been answered, you can read up about them, and maybe if you don't have time to read them all, maybe copy them and so on. But I wanted to mention that because there's a growing number of questions. Do you have any others lined up, Sarah?
I've been answering some. So what's next on the list here? There was a question here from Tony Wilcox about converting hydrogen back to electricity, a reversible electrolyzer. Have you guys run into that? I know that Jeff's company is looking at skids for electrolyzers right on site, but could you actually make that into a generator as opposed to trying to feed it into a combustor?
So that's the reverse of an electrolyzer is going to be the fuel cell, right? So I think I'm not I'm not familiar with the technology of electrolyzers. I simply look at them as a way to convert water, for example, into hydrogen. I do believe that there are companies that are looking at devices that can, in and of themselves, do both conversions. In other words, convert to hydrogen and then take the hydrogen and reuse it back into, in essence, what is a fuel cell. So I would say I've only read about those things. It seems certainly doable. And again, we're just a little bit at the beginning of this journey with the investments in technology. You'll see all sorts of approaches for electrolysis. There's 4 or 5 that I can think of off the top of my head, that technologies that can be used today. So very exciting. I believe it's doable. I like the approach. The one thing, Sarah, if I could go back to the question and just add to what John said about hydrogen and natural gas. I view what happens in Europe here when it certainly came to renewables. It was a bit of a harbinger of what is happening in the United States today, and I see also the similar with hydrogen. Here in the Netherlands and in Belgium, but in the Netherlands and Germany, they're already building out a unique hydrogen pipeline infrastructure. And I suspect with a reluctance in many parts of the United States for new gas home hookups, the push will be away from natural gas towards electrification. And then they would be a hydrogen infrastructure. What I would say, there are already thousands of miles of hydrogen pipeline infrastructure. The majority of it is in Louisiana and Texas, but there's some in Los Angeles as well. This is infrastructure by companies that produce hydrogen and sell it to various industrial companies for their various processes. So it is being handled today safely. There are standards in volume, and they're looking to invest and build out that infrastructure. So I see more of a unique type of eventual hydrogen pipeline infrastructure.
I see a
Very
question
good question.
that's been open with which James Harris had put. What green hydrogen startup do you see having good prospects? And a few folks have put in, David Wall said, check out Blood Power. Shannon said Bloom Energy. I'm sure their viewers and the speakers may have others. So it's an interesting, one of the things listening that I think is a very real factor in the next few years is if one looks at where discussions were about a lot of the things that are being used right now, where they were 5, not to mention 10 years ago in terms of cost, practicality, it's a sea world, it's a huge change. So I suspect that now as this is getting taken really seriously, and as you mentioned, Jeff, the amount of money being directed at this is, pretty serious money. I suspect that it's very hard to predict where even 3-5 years from now, we're going to be, there was a publication recently about how electrolysis processes, there's a, new techniques being tried out that raise the efficiency, fairly dramatically. So I think it's a pretty exciting field in general. But having said that, we should go to additional viewer questions. Sarah, do you have any that are lined up?
There was another live one up top.
I'm sorry, which?
There was another live question to be answered live up top. I'm reading the rest of the ones.
I see.
We are not going to answer about use in homes.
There was one about microgrids.
Yes,
that I saw, and I did make a quick answer, but not a very good one. Can I speak on that one?
please. And do you happen to have it up so we could say who asked it? No. Go ahead.
No, I don't.
Go
it
ahead,
was one
John.
of the. It
Go
was
ahead.
an early
Go
question.
right ahead.
Microgrids, if you don't know what they are demand DER, demand side resource, where they would be able to provide an isolatable source of electricity for a small group of users or a group of industrial users or so forth. And the utilities are eager to have those available because they have a new thing they measure now. They call it flexibility. They know they're going to need to 25% of their energy is going to have in 2050 is going to have to be absolutely manageable. They're going to have to move it to a different time, or they can't eliminate it, but at the same time they can't accommodate it when the demand comes. So they're going to have to move it to a different time. Microgrids are the way they intend to do that. So there is some research going on now where a microgrid would have a portable electrolyzer and then make electricity with fuel cells, so that it takes electricity off the grid to make hydrogen, but then it runs its own electricity plant using fuel cells. And that is just a wonderful thing for grid management. And I really hope that things like that are going to happen.
That's great.
I will tell you, John, that San Diego Gas and Electric is doing that right now. That's as part of their sustainability plans is exactly that type of microgrid.
We have done a webinar on microgrids earlier in our series, and we certainly will come back to it again because I think it is a growing thing. There's a question here from R. Harvey about if electrolyzers are powered from the intermittent renewable power, does the intermittency interfere with the operation of or shorten the lifetime of the electrolyzers? Do either of you know that? I'm sorry, it doesn't directly.
Yeah, I think I know what is the question is. I think I'm not totally versed, hardly versed in electrolyzers. I do know many of the types of technologies like or can run with variable power. Some technology electrolyzers like to run at full load all the time, and it would really be a function of the power company making sure that they'll be able to modulate and provide the amount of power necessary. That's basically what I can say about that.
That is one of the design considerations, and
Right.
that they are moving toward electrolyzers that will be able to tolerate those variations because of exactly what the participant said.
Very good. Well, I want to, we're just about at the end of the hour. Yes, the issues about supply of hydrogen are really important, and I want to thank the speakers for their presentations. I don't think, I think it's really interesting that they are talking about hydrogen in electric equipment that's already there, that's an asset already built, is a very interesting way to do a transition, and that it's probably pretty feasible. We know that transportation is asking for hydrogen for cars and things. Toyota and a couple of other companies are, and the Olympic buses that were just happening at the Beijing Olympics are being run on hydrogen today and fuel cells, changing hydrogen back to water and using that electricity. So I want to thank you all, and thank you to speakers. I think this was great, and it also just shows that we really should try and find some alums who are expert on hydrogen supply. The EESN, the EESN is a network of groups of alums around the world who are working on energy issues, environmental issues, sustainability issues, and our purpose is to get those folks together in groups. And each of those groups is working on different aspects of the complex problem we have in trying to get to 2050 with a livable environment. So I want to thank you all. I want to suggest that setting up webinars with us. Again, we're trying to not only inform, but to connect alums and to make these groups that can try and build some solutions, or at least work through some of the solutions. A very active group in the network, two very active groups in the network, are advocating for US policy changes. I hope that we can get some more European groups. The Club of Germany this week is doing a seminar on plastics, the problem with plastics. So I hope you all will keep an eye on our website. Amy, if you could there it is, there's our website address. So we encourage you to come to the website, to join at least our mailing list and find out what our webinars are doing and get our emails once a month. And then especially if you're an MIT alum, go and make a group. Do it with other people in your neighborhood and other people in your business. And I think there's an awful lot that we've gotten started here, and we can really make a contribution to how we get to 2050, how we get to 2050 in a clean mode, one that perhaps we haven't lost all the corals, and perhaps the Gulf Stream hasn't shut down and made Europe freezing again. So I want to thank you again all for coming. It was just a pleasure to have you all here, and we will try and get a look at these questions afterwards, although we will not be responding to the hydrogen supply ones. That wasn't our purpose today. Thank you very much, everybody. And thank you, Jeff, and thank you, John.
Thank you
for that sentiment. Welcome to, thank you to everyone who signed up and participated, and Jeff and John for all your great information and all these great questions that it generated. So I think it shows that this topic isn't going away. It's coming back in the not too distant future for more discussion.
Yeah.
Thank you.
Thanks, everyone.